Good. So this week we're very happy to have Elena Kosygina from Purdue College, who will tell us about from generalized Ray-Knight theorems to functional limit theorems for some models of self-interacting random walks on Z.
Hello to everybody. I don't see anybody. I see just my screen. And but thank you very much for coming to the talk. And let's begin. I'll begin with my collaborators who contributed to various parts of this talk. And that's Martin Zerner from Tübingen, Dmitry Dolgopyat from University of Maryland, Tom Mountford from EPFL, and Jon Peterson from Purdue University. And the new results, which I will talk about in this talk, are joined with Tom and Jon. And it is especially nice to have this talk today because tomorrow, Tom turns 60. Not 60 factorial, but 60. Tomorrow is Tom's birthday. And it's nice to talk about just one side of his many research interests. So happy birthday to Tom. So I'll start with a review of squared Bessel processes because they are important players in this game. So B is a standard one-dimensional Brownian motion. D is the dimension. In this case, we look at the generalized dimension, so it's any number in R. And X is a starting point of a squared Bessel process of dimension D. And we'll denote it this way, where dimension is in the superscript and the starting point is in parentheses. And it's a solution of the stochastic differential equation written here with the initial condition X. I know that some of you are used to have absolute value. For all our purposes, this will make no difference. The only difference is that when the dimension is negative, this particular definition after the first heating time of 0 becomes, so the process becomes degenerate. With absolute value, the situation is different. But we will always stop our process if the dimension is non-positive upon the first heating time of the origin, so that difference will not matter. And this process will be called Bessel squared process of dimension D starting at X. So it is, again, common knowledge that for D natural number, this process is just the square of the distance of a standard D-dimensional Brownian motion from the origin. If you want to start from a different X, you just start it somewhere from a sphere of radius square root of X. For dimension 0, this process multiplied by a constant arises as a scaling limit of a critical Galton-Watson branching process whose offspring distribution has variance nu. So if you put nu over 4 in front of y, 2 will be erased, and nu will come here. Then that such process arises as a scaling limit of a critical Galton-Watson process with this variance. And there are many properties. I just want to remind 2 of them is that if the dimension is at least 2, then the process, even if it starts at 0 for all positive time with positive probabilities, stays above 0. If dimension is less than 2, then even if it starts with a positive number, it hits 0 in finite time with probability 1. And and if D is 0, then the process gets absorbed the moment it hits 0. If it starts with a positive X, it gets absorbed the moment it hits 0. So 0 and 2 are kind of a critical dimensions here. And to explain the connection, and the connection between branching processes and random walk goes back, I think, to Harris. this particular connection is probably due to failure. So here on the picture, I sketched the simple symmetric random walk. Of course, we will not be interested in simple symmetric random walk, but we will be interested in similar connection for our random walks, for self-interacting random walks. So here I sketched a path. Down crossings are blue, up crossings are red. And I run the walk until the first time it hits a certain negative level, AM, right? And then I want to, again, remind you and set up the notation that at this time, if I look at the up crossings and consider this is as a zeros generation, first generation, second, and so on, then I will get a Galton-Watson process. So Zj is the number of up crossings from this level to the next level, right? Happened up to this first hitting time of AM. And I start my process with 0. So again, if you have not seen the connection, to explain it, I'll just put a picture here. So suppose I'm here, I'm looking at this point, and I know that the number, since I'm looking at the first time of hitting AN, then I have the number of up crossings is 1 less than the number of down crossings. And I will look at all possible down crossings at this level. This is generation, whatever, 0, 1, 2, 3. And I look at all up crossings before the first down crossing. Right here, there is 1. I marked it in red. The second down crossing, there was no down crossings from this level, no up crossings before this down crossing. Okay. Then for the third down crossing, I had 2 up crossings before the third down crossing and after the second. And for the last one, I also have 2 here. So we treat these as offspring of these particles. So we have 4 particles in generation, say 3, and we treat these particles, these up crossings, as progeny of these particles. And we continue like this. And if we want to use only up crossings, then for each down crossing, there is a corresponding up crossing, except say for the last one, because I have 1 more down crossing than up crossing. There we say there is an immigrant in each generation. Up to this generation, there is immigrant, and the Galton-Watson process apparently now has geometric distribution with parameter, geometric offspring distribution with parameter half, because number of successes before failures are given by geometric random variable, mean 0, variance 1. The only one thing I want to mention is that to the right of 0, of course, the number of up crossings is equal to the number of down crossings, because again, up to the first time of hitting this level. Therefore, we have no immigrants. So in all these generations, we have an immigrant per generation, and here we have no immigrants. So looking at this Galton-Watson process, well, Feller looked at even more general ones and observed that after rescaling, right, if you start, so AM is A time proportional to A times M, BM is proportional to B times M. And after rescaling, this process converges to a solution of this stochastic differential equation. This drift 1 is because of the immigrant in each generation up to here. And after that, we don't have a drift. That's why you see here an indicator function should have been of S. Right. And this is sometimes referred as to Feller diffusion or diffusion approximations. And you can recognize separately that this is a concatenation of a half of a squared Bessel process of dimension 2. Right? A half, because you see 2 is here. In squared Bessel process, you have a different, so it's this process is a half of squared Bessel process of dimension 2. And after we have no immigrants, it's a half of squared Bessel process of dimension 0, starting from wherever the process ended at this point. So it's a concatenation of two halves of square Bessel processes. Now, why am I bringing this up? What will come at the end of the talk? Suppose we all know how to compute the probability that simple symmetric random walk hits AM before BM. And we know many methods. One can use branching processes to compute that probability. It's crazy for simple symmetric random walk, but you can observe that random walk hits AM before BM if and only if this process dies out before this generation. So the process hits AM before BM if the corresponding branching process dies out before this generation. Right? And if we want to know the time when we hit, then it can be expressed as AM plus twice the total progeny until extinction of this process. So, and then this is the key to, can be used as a key to much more general random walks, and will allow study of related branching processes, will allow us, for example, to couple our fancy random walk with a candidate for functional limit, candidate limit process in the functional limit theorems. So, but we will be interested not in, okay, simple symmetric random walk, the scale converges to Brownian motion, but we will be interested in a different limiting process, Brownian motion perturbed at extrema. So Brownian motion perturbed at extrema has two parameters, alpha and beta. Both of them should be less than 1, and it is defined and exists as a unique pathwise solution of this equation. So alpha I put in front of the supremum and beta in front of the infimum, and the standard sort of Brownian motion perturbed at extrema starts at 0. This process was introduced by Jean-François Le Gall in 1986. I have not seen his notes, but they are quoted in various papers, and then studied by many authors for various reasons, in particular Burgess Davis, Perman and Werner, Carmon and Petit-Dior, Chaumont and Donny, and Yu and Hu. So this is by itself an interesting process. And if we denote by S the supremum and by I the infimum of this process, then while the original process is not Markovian, the triple is a Markov process. And it is natural to allow this process to start not from just 0, 0, 0, 0, 0, 0 as here, but it's natural to allow an arbitrary starting triple as long as the infimum is less or equals than W is less or equals than supremum starting point. When I say standard BMP, I will mean starting point 0, 0, 0. So you can see that you have a infimum, supremum, and in between the process moves as a Brownian motion and receives pushes only when it hits the boundary of the range. So Brownian motion perturbed at extrema is a good candidate for limiting process for a good number of random walks. And I would like to mention first that one can obtain it, probably the most simple way to obtain Brownian motion perturbed at extrema as a limit of a random, some kind of random walk is, well, this is as a limit of perturbed random walk, or also a limit as once edge reinforced random walk. So recall that we have these two parameters. Oh, by the way, I want to mention that it is completely obvious that the process does not exist for alpha greater or equals than 1 or beta greater or equals than 1. But what is not obvious and why these papers were necessary, that it's not obvious that it exists for the full range of parameters, alpha less than 1 and beta less than 1. Why it's obvious that it doesn't exist for alpha greater or equals than 1. So if we just cover up this part, if alpha is say 1, we take supremum, we take this supremum to the other side. If alpha is 1, then you get process minus its running maximum. It's strictly non-positive process. And it cannot equal to Brownian motion, because Brownian motion, it's, you know, Gaussian distribution supported of the whole R. So the fact that this is necessary is obvious, but sufficiency and construction were non-trivial matters. So here, given alpha and beta, if I want to get a random walk which converges to Brownian motion perturbed at extrema with these parameters, one can simply do the following: start at 0 with probability half and half, move to the left and right at the first step, and then move a simple symmetric random walk on the range between the maximum and the minimum of the range, and move to the right with this probability and to the left with a complement probability when you are at the right end of the range, and similarly at the left end of the range. You might be wondering why here I have 1 over 2 minus alpha. This actually very simply, and how this parameter alpha arises in this limit, you can notice that once you come to the boundary of the range, you don't necessarily jump here. It takes you geometric number of attempts to increase the maximum to the next one. So if you have a drift, so if this is P, right? So your drift is 1 over 2 minus alpha times 2 minus 1, right? So that's 2P minus 1 drift. And then it takes you geometric number of attempts, right? Geometric distribution with parameter 1 over 2 minus alpha has mean 2 minus alpha, the reciprocal. And when you calculate that, you'll get alpha. That's basically how this parameter alpha arises in Brownian motion perturbed at extrema. So this walk converges to Brownian motion perturbed at extrema in the standard Skorokhod topology. Right. But then we know that Brownian motion has first and second Raynight theorems. Raynight theorems also hold for Brownian motion perturbed at extrema, and this was proven in the work of Carmona, Petit, and Yor. So suppose capital L is the local time of Brownian motion perturbed at extrema at point A up to time t. And for x non-negative, denote by tau A of x the first time when the local time at A exceeds x. And Raynight theorems state that the processes, when you run from A forward and backward, are independent squared Bessel processes of appropriate dimensions. So more precisely, so before I put the text on, I'll show the picture. So I have Brownian motion perturbed at extrema, and A is somewhere here, doesn't matter where A is. And I'm looking at the first time, so my Brownian motion perturbed at extrema is not pictured here, but I'm looking at the first time when the local time exceeds x, right? And then I'm looking at the local time of this process in this direction. That's indicated by y with the left arrow. The claim is that the resulting process is Bessel squared process of dimension 2 beta, with initial point, with a starting point at x. Now, if we look to the right, the corresponding process of local times is a concatenation of 2 squared Bessel processes The first one is starting at the same x with dimension 2 times 1 minus beta. And at this time, it loses, so it changes to Bessel squared process of dimension 2 alpha, right? Remember, if alpha and beta is equal to 0, we have standard Brownian motion. So for Brownian motion, we have 2 and 0 respectively. 2 here, 0 here. This is just, yeah, and 0 here, right? So this is what's written on this slide, that for fixed alpha and beta, and I took, for my convenience, I just took a less than 0, and then the local time processes, this y and this y, are defined as going forward and backward from point S. And this S is actually a space for my original process and time for my Ray-Knight theorems. And then the claim is that the processes are independent. So given X, the processes with arrow forward and arrow backward are independent. The one with our arrow backward is Bessel squared of dimension 2 absorbed upon hitting 0, starting at X. And the one with the opposite arrow is a concatenation of Bessel squared process of dimension 2 times 1 minus beta starting at X. And then after time absolute value A, Bessel with squared process of dimension 2 alpha, right, absorbed upon hitting 0. Right, so in short, Brownian motion perturbed at extrema has Ray-Knight theorems. So there are Ray-Knight theorems for Brownian motion perturbed at extrema. And similarly, we can start Brownian motion perturbed at extrema not at 0, 0, 0. We can start it at, say, negative 0.5, 0, 0.5. And then this is pictured for starting point x equals 0 for the first heating time of negative 1. And then it's going to be a concatenation of 4 processes. First, it's 2, 1 minus beta. Then this is a original minimum. Here we have the same thing as for Brownian motion, Bessel squared of dimension 2. Then it switches to Bessel squared of dimension 0. And then upon reaching the original maximum, it becomes Bessel squared of dimension 2 alpha. So these are Ray-Knight theorems for Brownian motion perturbed at extrema, starting from an arbitrary triple. Now, where such things come into play, so after, essentially at the same time as Davis's work, within a year, Balint will correct me, within probably a year or so, there is a much more general model for which I'm using terminology introduced by Balint Todd. There are generalized Ray-Knight theorems. So what are generalized Ray-Knight theorems? They are diffusion analogs of Feller diffusions for more complicated self-interacting random walks. So here is one model that was considered by Balint Todd in 1996. So it's a nearest neighbor random walk, and it's defined by a certain weight function, which roughly speaking behaves polynomially in this way. So when gamma is 0, so it converges to a constant and then goes to infinity. So it's called asymptotically free case. And when gamma is positive, it will be referred to as polynomially self-repelling case. So given a weight function, we define the probability to jump to the right, given all the paths of the walk. So it's a highly non-Markovian. The weight function evaluated of number of crossings of a set xn plus 1, crossings both ways, from xn to xn plus 1 and from xn plus 1 to xn, divided by the number of crossings of xn, xn plus 1, and xn, xn minus 1. Right? This is a reinforcement structure. When gamma is positive, then the walk is, the more it visits, the smaller is the W, well, depending on the constant C here, of course. So polynomially self-repelling case corresponds to gamma positive, and asymptotically free case corresponds to gamma equals 0. So in these two cases, these two cases were considered in this paper in detail, and Balintov proved generalized Ray-Knight theorems for this random walk in the same sense as I started, as at the very beginning, as I explained for the simple symmetric random walk, that the corresponding processes of up crossings or down crossings after rescaling converge to Bessel squared processes of appropriate dimensions. And he was able to recognize the fact that the limiting diffusions he obtained completely match those for Ray-Knight theorems for Brownian motion perturbed at extrema with corresponding parameters. I'm not stating here parameters, but, and then it was natural to suggest that maybe these self-interacting random walk have scaling limits, and there is convergence to Brownian motion perturbed at extrema. And indeed, he was able to prove not the full result, but he was able to prove that using these Ray-Knight theorems as a tool, he proved the convergence in distribution as A goes to infinity of these processes, where tau S over A is an independent geometric random variable with this mean. So it's almost the convergence of one-dimensional distributions. Almost the convergence of one-dimensional distributions, but he used Laplace transforms, and this is how the result stands up until now. It's still the weak convergence question of even one-dimensional distributions or functional limit theorem is still open, and for Tom, John, and me, it's we consider it as a work in progress already for some time. But today, I'm not claiming the result yet. I did not say that you can interrupt me at any time. I really much prefer interruptions and just speaking to essentially myself because I don't see anyone. Are there any questions so far? Okay. So another model of random walks which interact with their own history is excited random walk, and I'm looking at excited random walks on Z. So they are also called cookie walks. Originally, they were introduced by Benjamini and Wilson for in any dimensions with a restriction of a single excitation, and then extended by Martin Zerner to multi-excited random walks in random environments. And they were extensively studied over the last now almost 20 years. So we are on Z, and at each point Z over integer lattice, we put a collection of what is sometimes called cookies, maybe infinite collection of cookies. And each cookie encodes the probability to jump to the right upon, say, the first visit. You eat the first cookie from the bottom of the pile and determine what is the probability to jump to the right. When you return to this point again, you eat the second cookie, so cookies disappear, and jump to the right with this probability. If you return third time, you jump to the right with this probability, and so on and so forth. So W sub Z is a stack of cookies presumably infinite stack of cookies at site Z. And I indicates that this cookie is eaten upon the ith visit to a site.
Sorry, could you please repeat the mechanism of the cookies, because there was an interruption with your microphone and we couldn't hear you very well. Thank you.
Yes. So the mechanism is the following. So we have a site of the lattice Z, and we see that there is an infinite, and we say that there is an infinite stack of cookies piled up on top of this, of each site. So the random walk, say, comes to point Z for the first time, eats the cookie from the bottom of the pile, and jumps to the right with probability encoded by this cookie. So cookie is the probability to jump to the right. The ith cookie is the probability to jump to the right upon the ith visit to a site. Does that make sense? If the walk returns second time, it uses the second one. Third time, it uses the third time. And of course, once cookies are eaten, they disappear from the pile. And this is for each side of the lattice. For each side of the lattice. So the walk keeps eating cookies and deciding to jump to the right or to the left, nearest neighbors, with probabilities encoded by these cookies.
Okay.
So more is that okay?
Yes, thank you very much.
So more specifically, say we start the walk at 0, and then given how many times the current site is visited, it is the j's visit to this site, then the probability to jump to the right is wx of j, and complement probability to jump to the left. And the averaged measure for this process is defined in this way. So if you have a set which is represents an event relative to paths and in both paths and environments, then its expected value with respect to the measure on cookie stacks of this P0W. P0W is called quenched. And we assume that cookie stacks are IID under this probability measure on the environment. So this is our assumption. We look only here on one-dimensional models. Well, there are various types of this model. First of all, if we bound the number of cookies per site by some number, say m, that's what we call IID bounded cookie stacks. This model was studied, the most studied model, and a lot of known about it. Then Gadi Kosma, Tal Orenstein, and Igor Shinkar asked the question, what if the cookie stacks are not bounded, but they are periodic, like 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on? What can we say about random walk among such cookies? And they used actually Lamperti's method of Lyapunov functions and the correspondence with branching processes, but not so much with branching processes, but with up crossings and down crossings picture. And they were able to prove recurrence and transience for periodic cookie stacks. Then with Jon Peterson, we considered IID Markovian cookie stacks. Well, it's an obvious generalization, obvious in terms of it's obvious to generalize and not to prove of periodic conditions. So we took, I will introduce this model in a moment. And it includes periodic case and also some models with bounded cookie stacks. And there is a curious model of p-rotor walks on Z. I'm mentioning it because it's a degenerate, non-elliptic excited random walks with Markovian cookie stacks. It's representative of the same model, but it's not covered by our results because of degeneracy. And then Nick Travers considered bounded cookie stacks, which are not IID from site to site, but Markovian. There is a stationary Markov process across Z. So there are lots of, there was a lot of work done, but today I'm concentrating on a recurrent case, right? So there are conditions for recurrence and transience. So I will only talk about recurrent case. So, but what do we mean by recurrence to begin with? We have non-Markovian situation. By recurrence, I mean that lim_inf is -infinity, lim_sup is positive infinity with probability 1. And this has been proven. We have 0-1 laws for this kind of walks. So when I say recurrent, it means lim_inf is -infinity, lim_sup is positive infinity, and the starting point is visited infinitely many times with probability 1. So suppose we have bounded cookie stacks, meaning that there is a constant m, so that in your infinite pile of cookies, each cookie after the mth one actually should be strictly greater than m here. After the mth one has drift 0. So you can think that you've eaten m cookies and no cookies left. You just make an unbiased jump from that side from now on. And the main parameter there is, this is a drift stored in the ith cookie. This is the expected total drift stored at site I. Since we assumed IID, doesn't matter which I we take, we get this parameter. And it is known that from our work that this random walk is recurrent if and only if this parameter in absolute value is less or equal than 1. And then when I gave a talk at some point about recurrence and transience of University of Maryland, after the talk, Dima Dolgopyat said that, you know, I think that in the recurrent case, the limiting process should be Brownian motion perturbed at extrema. And this is the first time I heard about Brownian motion perturbed at extrema. And if I put this theorem here, because in bounded cookie stacks case, it is, you can basically sense it. It's very simple to visualize why Brownian motion perturbed at extrema is the limit. Because if you run your cookie walk, there is a natural range. And since it's recurrent, it essentially eats all the cookies in the range. Most of the cookies in the range, there is a little bit left here, a little bit left there, but in the bulk, in between the minimum and the maximum, it behaves as simple symmetric random walk and receives a push only when it comes in the vicinity of a maximum or vicinity of a minimum. So it is natural that when you rescale it, divide by square root of n and speed up time by a factor of n, you get Brownian motion perturbed at extrema with these parameters, right? So why these parameters? Because you essentially eat all the cookies, right? If the total drift stored at each site is theta, then, and the range is of order square root of n, so the answer is natural. This was extended to unbounded random M with power tail by Omar Chaktoon in his PhD thesis. If I did not know this result for bounded cookie stacks, I'm sure I wouldn't be able to even, at least I wouldn't be able to figure out that in other cases, Brownian motion perturbed at extrema are also a good candidate for the functional limit. So what is a Markovian situation? I take finite state space, so finitely many states, K is a matrix of transition probabilities on this finite number of states. Eta will always be an arbitrary initial distribution on a state space. And P is a function which says, if I'm in this state, what is the probability to jump to the right? So it's an arbitrary function with values strictly between 0 and 1. So I assume uniform ellipticity here. And for each X and Z, I construct a Markov chain, independent Markov chain on given this data, right? Starting with eta initial distribution, I construct a Markov chain, and I use a function p to generate my cookie stacks. Right? So I have IID Markov chains, and the probability of random walk to jump to the right is given by p evaluated at whatever state is at the j's visit. So this gives us a cookie environment. And our assumptions, apart from those which I already listed, is that this Markov chain has only one irreducible closed subset, right? Could be absorbing state, it could be a reducible Markov chain. But the thing is that there is a unique stationary distribution supported on this irreducible closed subset. Right? So this is the assumption on Markov chain. And Jon Peterson and I were able to basically characterize the behavior of excited random walks in these cookie environments. First of all, mu is the invariant measure, and for this invariant measure, we can calculate the expected probability to jump to the right, p bar, right? So it's with respect to this invariant distribution. And then there are two critically different cases. P is not 1/2 and P is 1/2. When P is not 1/2, then for any initial distribution, the walk is transient, ballistic, has a linear speed, depending on P is greater than 1/2 or less than 1/2, and satisfies the classical central limit theorem with respect to the averaged measure. Everything we do here in terms of limit laws is with respect to the averaged measure. If P bar is 1/2, then there is a variety of different behaviors which are characterized by two parameters, theta plus and theta minus, and they are given by explicit formulas which look horrible, but they are explicit in terms of K, P, and eta. These parameters provide a complete characterization, recurrence versus transience, ballisticity, and a type of limit law in the transient case. We were not able, in this paper, we did not treat the recurrent case. And our next step was to actually try to treat the recurrent case. And our sort of assumption was that a good candidate for the recurrent case was Brownian motion perturbed at extrema with appropriate parameters. This is instead of alpha, and this is instead of beta. Now, but what are these parameters and where do they come from? So two parameters, plus and minus, come from considering a single cookie stack with initial distribution eta. Right. So UN is the expected, so I'm looking at the single cookie stack and I'm computing the expected number of up crossings of a walk before the nth down crossing. This is a standard thing to do. And dn, the expected number of down crossings before the nth up crossing. In some sense, there is a lot of symmetry between these two things, and it can be shown that in this case, these limits, the variance of un and dn divided by n, converge to the same constant nu. And this is a total excess. So this is expected number of up crossings before the nth down crossings minus n, right? This excess multiplied by 2 over nu converges to theta plus, and this limit exists and is a number, and multiplied by 2 over nu, it's denoted by theta minus. Sort of it's excess of expected down crossings over the over n. It can be shown, but I don't have an intuitive explanation for it, that these two parameters add up to 1 minus 2 over nu. In case of simple symmetric random walk, when there is, of course, this is 0, or in case of bounded cookie stacks, this is also 0 because nu is equal to 2. And excited random walk is recurrent if and only if the maximum of these two parameters does not exceed 1. Right? This maximum need not be non-negative, can be negative, it's okay. So once we characterize, we know the recurrence region, it's natural to state this functional limit theorem, which we proved with Jon in periodic case, and it took us many years to figure it out in the general Markov case. Basically, the main result for this talk and is the result, the convergence to Brownian motion perturbed at extrema in the general Markov cookie stack case. But the theorem looks exactly the same as before. We rescale random walk properly. Now here we have 2 over nu. Before, previously with bounded cookie stacks, nu is 2, there was nothing here. And this process converges in the standard Skorokhod topology to Brownian motion perturbed at extrema with parameters theta plus, theta minus. In the periodic case, we know we have an explicit formula for nu, and we know that it's always just from this formula, less or equals on 2. Now, what's for us, the transition from this case to this case was completely crucial. We were stuck for a long time. And it is sort of addition. It is Tom Mountford who got us unstuck, right? So now let me try to tell you in the leftover time what is the way for bounded and periodic cookie stacks of getting the functional limit theorem, and what is the way we ended up doing. What is the idea of the proof for Markovian cookie stacks, which is completely different from this one?
Can I just ask a question about the statement before?
Yes, absolutely.
So if you started the Markovian cookie stacks at an invariant distribution for the Markov chain, you wouldn't expect to see this, right?
If I start from the invariant distribution, I would expect to see this with non-trivial theta plus and theta minus, except for trivial case of simple symmetric random walk. So it's a very good question. So if I start with the invariant distribution, mu, 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 product measure, I will get non-trivial theta plus and theta minus.
Oh, really? Okay.
And the reason for that, I'm going to address that. It seems because the correct invariant distributions from the point of view of the walk are not mu.
Ah, okay.
It's not mu. So if you start across with mu, typically you would get non-trivial theta plus and theta minus, with the exception of like simple symmetric random walk case, and yeah.
But maybe there is some distribution you could. Is there some distribution you could start them with? Okay.
Absolutely, you are absolutely right.
Okay.
All right, I'm about to say that yes, but we don't use it, right?
Okay.
Yes, there is a invariant measure from the point of view of the particle, and it's a product measure. And if you start with that product measure, which is not identically distributed, saying you will converge to Brownian motions, both theta plus and theta minus are 0. Yeah.
Okay, thanks.
There is such a thing, but if I get there, I'm planning to get there actually, because I have very general overview of a method, and not any particulars. The paper is 60 pages long, so so for bounded and periodic cookie stacks, the idea is very, very simple. You take random walk and you look at its increments and you do basically Dub's decomposition, right? You subtract the quenched expected drifts and then add them back. So this process is a martingale, we call it Bn, and this is the drift eaten, Cn for cookies, right? So we show that this martingale has quadratic variation of order n. Actually, for bounded and periodic cookie stacks, it is divided by n converges to 1, indeed. And for these ones, if you imagine bounded cookie stacks, so for bounded cookie stacks, as I said, you when you are recurrent, you eat all the drift in the range. So Sn minus In is exactly the range of the walk. And how much drift have you eaten? You've eaten the drift of order delta times the range, right? And then you see that after rescaling, you get delta and minus delta as the parameters of your Brownian motion perturbed at extrema. You need to do the work, but sort of the idea and decomposition is very, very simple. You do Doomb's decomposition, martingale plus something else. And this something else is easily identified to be of the form you actually want. For periodic cookie stacks, it's a bit more complicated. It was not obvious at all because you've never finished eating the cookies. And when you are in the middle between minimum and maximum, the environment keeps changing. So what worked is that we were able to decompose Xn as Bn, this same Bn. And then what we did, we subtracted Xn from Sn and Xn from In, but the parameters here are different, so you don't get the range, you get something else. The quadratic variation of this martingale is nu over 2 times n, approximately. And then using the fact, our relationship between theta plus, theta minus, and nu, and rescaling. So now, as you see, Xn appears in both sides. If you take it in to one side and recalculate and use this connection and rescale, then you will see the emergence of exactly what is claimed in the theorem, Brownian motion perturbed at extrema with theta plus and theta minus. But the decomposition is a bit trickier, right? Sn minus x, capital Sn minus xn, it means that if you are sitting at a point, you are looking at up crossings to the right of you, and you are studying this thing using branching processes looking to the right. And if you are sitting at X and looking at this, you are studying branching processes to the left of you, and right, and using those to get the result. So the implementation of these ideas is based on the study of processes of up and down crossings and generalized Raynight theorems, which we proved for bounded cookie stacks with Thomas Mountford and for periodic or Markovian cookie stacks with Jon Peterson. Now, for Markovian cookie stacks, everything, absolutely everything works. There is one little lemma which fails. And it fails for a reason, because fluctuations of these ones happen to be of square root of n due to our Markovian periodic are not non-random cookie stacks, but these fluctuations of these things are of order square root of n, and this Brownian motion does not capture the whole Brownian motion, so to speak. And that's why we were stuck. We tried annealed averaged martingale decomposition. Why do we subtract quenched? We can subtract annealed. And this actually works for rotor-router models in one dimension. It works like charm. In our case, we get, if you condition on up crossings, down crossing, knowing up crossings and down crossings, it gives you so much information about the environment that you are losing any control and any hope to have anything invariant. So the idea which worked is an old sort of school idea, is a coupling, right? So the idea was that we looked at our random walk only at times when it hit, so we call it mesoscopic sites, negative epsilon square root of n, epsilon square root of n, and so on. So we only looked at the times of visits to, to sites of order epsilon square root of n, of integer multiples of epsilon square root of n. This, so therefore we could introduce the walk, the scaled walk. We call it Mesoscopic Walk. And our hope was to do the following. We take Brownian motion perturbed at extrema with the right parameters, and you can discretize it in a variety of ways. Let's look at the first time when it hits minus epsilon or epsilon, and make a walk which converges weakly converges as a process to this. This is very easy. This part is very easy. But then what we actually did, we coupled this walk, this triple, with this triple. So, and we proved that the probability that the coupling is not broken up to time capital K, where K is arbitrary, over epsilon squared, converges to 1. The mean for this probability as n goes to infinity and epsilon goes to 0 is 1. And we also proven, so coupling is not broken, but if you couple the walks, that's not enough for functional limit theorem. You also need to know how long does it take for your walk to go here or there, right? So then there was a time control that the time it takes to make one mesoscopic step has a correct variance. So n epsilon square is the order, and then we have nu over 2 is the correct parameter, right? So we were able to prove these two statements, and then they give the functional limit theorem. So where is the difficulty? The difficulty is that at each step, you have to deal with random environment eaten by the walk. So originally, when you prove Ray-Knight theorems, the environment is IID and it's very nice, but after the walk moved for some number of steps from here to there, and you come to some point in the bulk, your environment is eaten up by the walk. So the picture, this is my last slide, the picture is pretty much like that. This is the minimum of your walk, this is the maximum of your walk. But you are somewhere, for example, in the bulk. Then what is the environment here? Here it's IID, eta, IID, eta. What is the environment here? One observation is that if you are here, then the last jump before you got here from the right was a down crossing, and the last jump when you got here from the left was up crossing, right? So therefore, if you ask yourself, what is the next cookie at x plus 1 if you jumped, the last transition was to the down crossing, right? So what is the next cookie after the down crossing? That is in itself is a Markov chain of the next cookies after successive down crossings. And this Markov chain is a finite state Markov chain, of course, and it has its invariant distribution. And this invariant distribution we call pi plus. Similarly for up crossings, right? What is the next cookie after the up crossing? And we call this invariant distribution for this different Markov chain, pi minus. And what happens is that if you take product of pi minus up to 0, mu at 0, and product of pi plus to the right, this is the stationary distribution from the point of view of the walker. So if you start your walk with this initial distribution, and you always look at it from the point of view of the walker, you will always see this distribution. And it is for this walk, you get Brownian motion, unperturbed Brownian motion. So the moral is that here, roughly, you get pi minus, here you get roughly pi plus, and you need to utilize generalized Ray-Knight theorems for corresponding branching-like processes to get, to prove the probability of exiting to the right or to the left and the time control. Thank you very much for your attention. I would be very happy to answer any questions you might have. I didn't want to go much more over time.
Thanks very much. Other questions? Unmute yourself and ask a question.
I want to stop sharing my screen just to see people because it's very lonely on this side. nowadays. You cannot look the audience in the eye. And yeah. So basically, yeah, I tried to concentrate only on recurrent case, and it really gave us a lot of trouble.
Can you say anything about like some kind of local central limit theorem for this?
I mean, this is, the answer is probably it is possible to do something, but we never tried, and probably we won't try, right? Because it's already managing what happens with random environment after it's being modified by the walk is by itself is quite complicated. And we had we known how hard how much time and effort it'll take, we probably wouldn't even have started, right? But the picture is nice. The end picture, I think, is very nice. And there is actually work in higher dimensions, but in those kind of special environments, specially constructed environments. I just don't want to use more time than, not by us, it's work by Swee-Hong Chan in particular, right? So, and Lionel Levine is there. It's centered around rotor router models. Yeah, there has been interesting progress there. Yeah. Any other questions I might answer for you?
I just want to make not a question, but about one of your references. You refer twice to two papers of Carmona Petit and Yor, and as I recall, you wrote R Carmona as if it was René Carmona, and actually it's Philippe Carmona, just to make it.
God.
I have to say that it's Philippe Carmona, not René Carmona.
Thank you. This is definitely, yes. When I typed the slides, and for my previous life, I believed it was René Carmona.
No, it's Philippe Carmona and Frédéric Petit with Mark Yor, of course. Yes.
Right. It's actually the same paper. I quoted the same paper twice. Yeah. But thank you. I will correct that.
These mistakes are made quite often, and probably it's not.
Yes, but I appreciate. I don't want to make a kind of mistake. It's the same mistake.
No, I'm sure. Yes. Sorry.
The same mistake with Kozlov, because there are so many. There are actually in Russia so many Kozlov who are mathematicians, and you need to pay attention which Kozlov you're talking about. Right? There is Mikhail Kozlov. There is Sergei Kozlov in random walks. We are talking about the same area. Yeah. Thank you, Balin. Yeah.
Can you say a word about the link with rotor router?
Rotor router, you mean in 1D?
Yeah, so that's yeah, I don't know what you mean by that. So
rotor, so in one dimension you have a sequence of rotors, just arrows pointing in
okay,
direction.
okay. So
and then when the walk passes, the router switches, but if it's defective with small probability p, it does not switch. So this way you have random environment, and once you given random environment, you have deterministic walk.
okay.
And in this case, there is also that kind of walk convergence to Brownian motion perturbed at extrema, once you start with the reasonable initial conditions.
Okay.
But in multidimensional case, what people do with these rotors, they make rotor to change, not to change periodically like in real router model, but they make it to change sort of to pick a coordinate. So it's a martingale, and then take a balanced step in a coordinate.
Okay.
Right, and in that case, they introduce sort of so-called native environments. Basically, they found environments such that which are invariant from the point of view of the walker.
Yeah. Okay. Okay.
They have spanning forests, uniform spanning forests, and in this case, they can prove the CLT, convergence of rescale, convergence to standard Brownian motion with some sigma in many dimensions.
I see. Okay.
But it does not prove recurrence. They have, say, in 2 dimensions, they have convergence to Brownian motion in 2 dimensions, but the recurrence is not known except for vertical horizontal walks, where finally it is known. Because Brownian motion in 2 dimensions doesn't, yeah. So
Yeah, well, that's
you
related.
have CLT, but you don't have recurrence yet. It's
Yeah.
open.
That's related to Alex's question about local CLT.
Right. But here in 1 dimension, things are, it's very special. We have nearest neighbor, and 1D, it's much more doable because due to this connection with branching processes or just coin tosses, basically, right? When you go to dimension 2, I like.
And anybody did anything on the strip? So
Yes.
when
Well,
you
well, Martin did something on the strip
Yeah.
Originally, and then Dima Delgapad has for recurrent excited random walks has results of CLT on the strip,
Okay.
right? With all positive cookies, though. Yeah.
Oh, okay.
Yeah, with all positive cookies. Yeah. So there is one needs a good model, good tractable model. So basically, that's what we are searching for to start to actually move in many dimensions.
Okay. Thanks.
Yeah. Thank you for listening.